Thanks, Stephanie, for inviting me to give a talk. Hi, so I'm here to talk a little bit about Blender. How many of you have heard of Blender before? Cool. Oh, you already have heard of it. Well, some of this might be old to you, but so let's get started. So what I'm going to talk about today is a little bit about me, talk about Blender, what is it, in a little bit more detail. I'm going to try to convince you to contribute to Blender, because Blender, I think, is a pretty cool piece of software. And then I'll take you through how you might contribute. So that's it, and I'll have a little bit of a deep dive into how the motion tracking works later in the talk. And then after, if you guys want, I can help you build it, or if you want to go through the source code, I can explain how some parts would work. So we can do that at the end. So who am I? So I used to work at Google. I worked on a bunch of stuff like Maps, Street View. I worked on Android. If you ever use Google Now, I was on the founding team for that project. I worked on Glass for a little bit, and then I left and I went to a startup that was actually founded here at MIT called Loku. We sold Loku to GoDaddy, and I'm their leading product currently. But more importantly, what have I done on the side? I've worked on the computer vision code for Blender's motion tracker, which is this component for inserting rendered footage on top of live action footage, and we'll look at that later. I also built this thing called Sarah Solver for doing nonlinear least squares optimization, sort of outside the scope of this talk, but at the end, if you guys have any interest in that kind of stuff, we can talk about it. I think it's really cool. So we'll talk about that later. So what's Blender? Blender is this integrated package that does a whole lot of stuff. It does modeling, it does rendering, it does animation, rigging, compositing, non-linear video editing. It even has a game engine in it, which is kind of crazy that this one package has everything. And that's why it's called Blender, because it's sort of all these components thrown into one big package and blended together. It actually gives it a lot of power because you can access a lot of this common functionality in one package, and most other things don't do this. So why should you hack on Blender? Blender is a pretty high-profile project. Not all of them are. Every month, about 500,000 people download Blender, so it's pretty big. There's not many packages that are quite so popular. Personally, I think hacking on Blender is really technically fulfilling. The challenges are pretty deep. There's a lot of sophisticated type algorithms that go on in there, spanning from sort of constructive geometry through advanced data structures for managing spaces. There's mesh algorithms, there's graph stuff, there's high performance computing, there's GPU, all that kind of stuff that you might want to work on is all there. Since Blender has so many users, anything that you do that's sort of on the critical path of what animators do potentially has a big impact. Myself, I worked on the motion tracking component, and I got a lot of feedback from the community that they really liked it, and I found this was pretty motivating myself. Community is also really nice to work with. This is a big bonus. Not all communities are. It's easy to get involved. People are pretty friendly, and they're happy to accept patches, happy to have people come in and propose changes. I found that this was pretty nice. Actually, it was so nice that I ended up going to Amsterdam to the Blender conference and have kind of turned some of those remote relationships into friendships. So with that, let's take a look at some of the stuff that's done in Blender.
Why don't you just admit that you're freaked out by my robot hand?
This is pretty freaky. It's not my fault, you know.
So this is a teaser from what's called an open movie from the Blender community. Blender is somewhat unique in that there's a foundation behind it that produces these things called open movies, where they don't just make a movie and then ship it, they also make available the full assets and production story alongside. So you can actually download the source for this and re-render it or mix it up or whatever. But yeah, the whole thing is done in Blender. So all the modeling, all the animation, all the compositing, all the editing, one package, all in Blender. So the caveat, not the sound, but the rest of it is in Blender. Actually, have any of you seen this before? No? Okay, check it out online. Tears of Steel, just look for it. It's kind of a fun little film. I'm in it. Not that I'm biased or anything. So you might have noticed there's some nice rendering in Blender. So this is one of the features that is pretty prominent. How many of you are familiar with ray tracing? Okay, well, there's a lot of different techniques you can use to render virtual worlds, and Blender is a fairly modern implementation that lets you make really nice photorealistic images, like this image of some fruit falling in water. It's actually a pretty active area of research. There's a lot of different stuff you can do in rendering, but Blender's implementation, simple physically based rendering, because it's simple, lets you do a lot of stuff easily. It sounds funny, but it's sort of the trend in rendering these days is this sort of path tracing solution that avoids all sorts of complicated stuff that used to be necessary. So an important part of making stuff in virtual worlds is to model stuff. You have to build geometry, and it takes a lot of work. Blender has arguably some pretty much best-in-class tools for doing modeling. It's extremely fast. If you talk to people in industry, there are some folks that use Blender to do frontline modeling before they bring it into other packages. Even if the rest of, say, their studio uses a different pipeline, they still model in Blender because it's so fast. Just the keyboard shortcuts are all set up in a way that's really efficient. It's really nice to work with. There's also a lot of pretty sophisticated geometry tools for building complicated stuff like cars.
You say fast and like algorithmically fast, or just like interfaces?
Actually, both. Algorithmically fast is only a bottleneck in some cases. It's usually restricted by people speed. Yeah, and so Blender has spent a lot of time making this quick. Like the movie stuff, you have the code of the animators and the modelers. So as you can imagine, there's a lot of tweaking to make things fast.
That's like usually the thing that open source software you can't get right.
Exactly.
That's the part.
Yes. Yes. Which is one of the reasons I think Blender is so cool, is that it's not just coders doing stuff because they feel like it. It's actually a group of people, artists and coders together who are trying to ship a product and end up producing something that's pretty production worthy. So there's this other part of making rendered stuff, which is that you have to make materials to go on top of your pretty models. And there's a bunch of different ways you can do it. There's shader-based language ones where you write code, kind of like what you do in an OpenGL shader. But there's another method in Blender, in addition to writing in your own language, which is you can construct these computation graphs where what you get as input is sort of a light ray that's hitting the surface, and then you get to control what happens with it. Is it attenuated? Is it scattered? Is there emissions? But essentially, you can glue together these little pieces, and as output, you get something like this lamp, where actually I don't know what. So I think this material is for the rust, and what you can see is it's putting together like a texture, which is probably the rust base, and then it has some glossy component for the shiny part of it, and the diffuse part probably for the rust texture part. Mm-hmm.
This might be a really nice question, but can you code it, or is there an API?
Yes, absolutely. Yes. This is ultimately compiled down to, well, it depends which backend you pick, but have you ever heard of LLVM? So ultimately, it's compiled down to sometimes it's shipped to the GPU and sometimes not. So the other part, if you have stuff that you want to render, you don't just want it to be static, so you need to put together some sort of animation. And when you see animated characters, you see a full-blown model with all the lighting and all the wondrous detail that's moving around. But it'd be really impractical to actually move around these incredibly detailed models. So instead, you build what's effectively a marionette underneath your detailed model. And then the marionette is kind of like bones, just like your own bones, except instead of being tuned for moving around in the world, they're tuned for the animators to tweak how things look. And here you can kind of see it that this character is from the second open movie, Big Buck Bunny. You can see the bones in his hands that the animators can use to put stuff together. There's 2 steps to this. One is you rig, where you put the bones in place underneath your detailed mesh. And then animating is usually done by somebody else, who will then control the rig to make animations that you see in the finished product. And Blender's animation suite is actually very good. It wasn't always, but in the last few years, it's become essentially industry leading. It's kind of nice. So not everything is super clean boxes and arch worlds. Often you have really rough textures or other such detail that you need to put into models. So Blender has this whole facility for doing sculpting where you can take a model and you can just draw depressions on it. So for this dragon, it's actually little scales that someone went in and drew with a tablet. I'm not set up to give a demo of it, unfortunately, but you can just rotate the model around and draw little scales on. And the way it's built underneath is actually pretty interesting. So sometimes you might have a huge model, and if you wanted to draw super detail everywhere, it would take up too much memory. But Blender has this sort of multi-scale implementation where they're able to store detail only where it's needed and not anywhere else. So it's algorithmically very fast and that's to work with because of that. Have any of you heard of ZBrush? So this is kind of like ZBrush, but in Blender, this is pretty good. Compares favorably with ZBrush.
So what do you start with when you start using the sculpt? Do you start with a dragon or do you start with a blob?
So that's a great question, actually. Usually people will start with something that's not a blob, but closer to their kind of final thing before they do the detailing. You can actually go full on just with the paint tool, start from a cube and just like sculpt everything out. There's all these facilities in Blender for what's called retopologing. Essentially, topology of the mesh, which is how the vertices and edges are hooked together, matters. And you can sculpt things in a way that'll create kind of like a gross mesh underneath, but then you do this thing called retopo, and it ends up with a really clean mesh. So people often iterate between retopo and sculpting to get really clean meshes with lots of fine detail. So the other thing Blender has that's kind of fun to play with is lots of physics simulation. You've probably seen lots of movies where there's exploding cars and waterfalls and things falling all over the place. So Blender supports all that, not just the rigid body stuff, but also cloth, air particles, the whole bit. It's all supported. Surprisingly, there's also a game engine. This is something that a lot of people don't even realize, but there's actually a built-in game engine. It's not too different from things like Unity. Have any of you heard of Unity or Unreal Engine? Yeah. So it's been around for longer than I think either of those. It's perhaps not quite as good in some senses, but because it's integrated with all these other tools for modeling and animating and all that stuff, it's actually very fast to whip together little demos. So a bunch of people have used this for some stuff. This is a screenshot from one of the open game projects, which is kind of similar to the open movie idea, but for a game. There's all sorts of other stuff in Blender too, so I'm not going to go through all of it. There's this whole UV unwrapping thing for peeling apart meshes so you can paint textures on them. There's the compositor where you can composite together many images to show, kind of like Photoshop, but as a program instead of as a single operation. Yeah, so there's a bunch of stuff. So the last thing I want to talk about is camera tracking. This is the one that's most near and dear to me because I worked on it the most. Rather than talk about it, I'll just show you. So I'll kind of narrate this video. It's a complete example of putting some rendered elements on top of some live action footage. The footage itself isn't that exciting, but it kind of captures the way it works. So this is Blender, and Sebastian, who made this video, brought up a little scene that he shot in an abandoned video. These little guys are trackers, and what he's trying to do is come up with a bunch of correspondences that go across frames. And you can think of it as input video, a bunch of pixels. Output from tracking should be a bunch of sequential XY positions for a single part of the physical world. So like, for example, this, well, it's kind of hard to. But you can see that the little squares stick to one part of the physical world, even though in the frame it's actually moving in 2D. And you can see that he's getting points all over the frame. And the reason for this is that we're going to reconstruct the 3D motion of the camera. And you have to get points that are all over the frame, both and far from the camera, in order to come up with an accurate estimate for the motion of the camera in the real world. Okay, so looks like, oh yeah, so this is showing one of these individual tracks, and now you can see that there's sort of enough tracks to reconstruct the camera. Actually, you don't need quite so many, but so the next step after you do the tracking is to solve for the camera motion. So that's what the sort of computer vision algorithm part that I wrote underneath does. And you can see here that there's this little set of points. Yep, those points are the estimated 3D position of each one of those track marks that you saw in the footage there. So each one of these track marks, one of these guys, becomes one 3D point in the viewport. And the kind of clever part that makes this all work is that there's a single static 3D position for each one of these guys that correctly matches the series of 2D locations in the film. Now, it takes a couple minutes of tweaking. There you go. Okay, so here it's working well. So you can see how these little spots pretty much match the footage when it's played. Okay, so this is really, that's at this point, the computer vision part is mostly done. And now the next part of this video is to show how to overlay some rendered stuff on top. So what Sebastian is going to do is he's going to put a monkey head, which is a primitive in Blender, on top of the box, and then put just some pipes connected to the box just to illustrate compositing footage together with rendered elements. Okay, so it looks like the track is all set, and you can see he was playing with the ground plane to make it easier to understand what's happening. And now he's going to make a proxy object. So if you want to put, say, a monkey head on top of the box in the real world, it would actually cast a shadow. But how do you make that shadow so that it looks like it falls on the box? And one way to do it is to make a proxy box, which is different, similar to the one in the real world, that you don't render the box, but you render the shadow. And so he's going to try to make it match pretty close, and then he will put a monkey on top in a moment, and you'll see when he does the compositing steps that, yeah, there's the monkey, that the shadow will get rendered by itself without the box. Okay, so now he's just playing around with the rendering, so there it is without the composite. And now, okay, this is the compositor where it's essentially lets you take each frame in an animation and kind of glue together various layers. So one layer is the background from the film. The other layers are things like the monkey head, the shadow from the monkey head, the fake box, which we're actually not going to render. And now Sebastian is just gluing it all together so that the shadow, which is just this part here, will be the only thing that's actually rendered over the footage. There we go. So now you can see monkey head placed. That RGB thing that he was manipulating just kind of manipulates the exposure. So if you see, in one of these scenes, you can see the camera path that was estimated. Let's see if it switches back. Yeah, see how that camera thing has a little tail behind it? That's showing the estimated camera path that the vision code found. It's just kind of cool to see how your hand actually moved in space when you're holding the camera. building stuff in Blender. This is really basic stuff, just making a spline curve, adding bevel, throwing a cylinder around it, maybe changing the colors. This is sped up, but actually not by that much. If you watch people who are really good at Blender, you kind of feel like it's a little insane how fast people can use it. I cannot use it this fast. Okay, so this is the final render. And yep, I think he's just setting up the final bits. In a moment, you should see the whole thing. It is just, he's setting up motion blur. It turns out motion blur is really important to make things look appropriate. Otherwise, you have your camera movement has motion blur, but then if your render stuff doesn't, it looks really weird. So it's important to have motion blur in your final rendered output. Yeah, just expose. Okay, so this is the final rendered output, and you can see that monkey head's been added. There's a shadow, the pipes. So that was a motion tracking component. Actually, we did the motion tracking component as part of a Google Summer of Code in 2011. I was mentoring Sergey, and we both built it together. Cool. Okay. So, any questions about that, by the way? It's all totally clear. You could re-explain it from scratch. So, I think you should work on Blender, and here's how you might do it. First off, you should download it and try it out. It's not that hard. It's a small download. 3 main things you need to do if you want to contribute is you should sign up for the mailing list, an IRT channel where they're pretty friendly. Create an account on developer.blender.org, which is the way where you'll upload patches. So unlike a lot of projects, Blender uses Fabricator. It's a code review system, project management sort of thing, ticketing and whatnot. Different than GitHub, which you might be used to, but I think Fabricator is actually really nice to use. Oops. And then finally, propose a feature or a fix or something on the mailing list, build it, ship it, and do it again. There's lots of projects to work on. So this is a link, and I think maybe Stephanie will send out the slides after. But there's a bunch of pages on the Blender wiki that describe potential projects you could work on. There's stuff scaling all the way down from small bug fixes to get your feet wet, which I think is a good way to start, to larger projects that involve adding broad new features, like adding more volumetric rendering support with some existing packages and whatnot that are bigger and more difficult features. Yeah, so I'm here to help you guys out. No pressure. Yeah.
I have a question.
Yeah, of course.
So, is there like a good unified tutorial that covers everything? Because there's lots that covers a few things.
Yeah. So the answer to that is Blender is a pretty large project. I mean, it has the functionality of something like 5 or 6 other pieces of major software in one package. So the answer is no, there isn't just like one tutorial that covers everything. However, there is a tremendous amount of excellent stuff online. I suggest Blender Cookie. Blender Cookie is a community resource where there's video tutorials, and not just like one snippet of a tutorial, there's like complete tracks. Like there's like a learn to model track that has a series of 10 videos, and you start out with like make a box, and then it's like make a box with like another box, and then make a box with a cylinder, and so on and so forth, until you end up with a cathedral. Same thing for animation, same thing for lighting, same thing for modeling, all that stuff. Some of the stuff on Blender Cookie is paid, but it's very cheap. If you actually want to work on Blender, highly recommend it. With that said, there's also lots of other tutorials on YouTube. BlenderNation.com is the community news source. There's lots of tutorials linked from there. I don't know if that helps. Oh yeah, so I also worked on the Sarah Solver project for those of you who are into numerical minimization. I'm not going to go into it a huge amount, but it's used for things like the lens blur feature on the Google camera. It's used for stitching panoramas. It's used for stitching all of the images on Google Maps, every Pano and Street View, a bunch of other places. It's also open source. Is potentially easier to get into, but it's more limited domain. So yeah, I think that's pretty much all I had. So questions?
Where did like the series come out of when there were already like other maybe more general purpose like minimization software? Like was it a performance thing or?
What other software are you thinking of?
I mean, like just like now ancient like Fortran code for like strain minimization stuff. I don't know, like they all have like their silly names, but like there's just like a lot of scientific stuff.
That's an excellent.
That probably doesn't work as well, but I was wondering. Like,
That's an excellent question. There's a couple reasons. Well, one was performance. That's a big one, but actually there was no package that does what Ceres does. So it's kind of unique. It has its own separate modeling layer that just doesn't exist in any of the Fortran stuff. It has integrated automatic differentiation, so it uses template metaprogramming to take the derivative of your functions without you having to do work. It has this whole layer for doing automatic sparse handling to efficiently deal with problems that look like they might be dense or really hard to compute, but we can compute them efficiently. None of the Fortran packages do this in a way that doesn't require the user to do a tremendous amount of work just to call the function that does minimization. Whereas with Ceres, you can do little pieces of your error function one at a time and not worry about how the variables are codependent. And Ceres just takes care of it all and ends up producing state-of-the-art performance. Yes?
So I really don't like anything about computer vision at all.
Uh-huh.
Like from the way you like in the room when you're doing the camera tracking, with the space, and essentially that maps onto a 3D model space, right? So like if you wanted to just use a video taken of walking through a room and like make like an approximate 3D reconstruction of that room, then you could do that with this, except you just have to sample points more nicely. Is that correct?
Yes, you could do it. It wouldn't be what I would, well, so the way you do that in Blender is you do exactly what you said. You just take a lot of track points, and then there's some functionality where you can draw a mesh on top of the track points. So you can use those little track points are what's called empties in Blender. You make lots of those, and then you can stitch a mesh together from them. And then there's another part of Blender where you can do what's called UV project, where you take several frames of the video and you project that onto the surface to get a texture. It's a little bit labor intensive. It's not necessarily what I suggest. There are other dedicated packages specifically for extracting dense models. That wasn't the focus for this because we were focused around building special effects stuff where you really need sparse reconstruction. That's, yeah, so it's a little different.
But don't the trackers have to be in all frames?
No, the trackers, you need to have some overlap. As long as you have at least 8 trackers that are always between, you could start out with 10 trackers, and then after 5 frames, if 3 drop, you're still okay. But if you add 3 more and then keep going, there's some continuity between the tracks. And if the tracks do a good enough job of covering the 3D structure of the scene, you're probably going to be okay. You can get into problems with drift if you have a long sequence of adding and dropping tracks. This can cause your final solution to kind of like your room will be like slightly not 90 degrees and whatnot. But you don't have to have a single, all the trackers don't have to be visible in all of the frames. Yeah, actually, so Ceres is used for the point tracking part. It's used for several parts of the computer vision code in Blender. It's fairly general purpose. Anything else?
Can you elaborate on the recompo? How does that work? And does it always create closed objects?
I believe retopo will, if you had problems with your mesh before, you'll have problems with them after retopo. So I think it will not change any of the correctness of your mesh. I think it will help you if you have Sometimes you can have vertices that have too many edges going into them and it can cause problems. Retopo will let you get rid of those. There might be edge cases where it doesn't work. I don't actually know that code very well.
Is there an existing process for taking in 3D scanned objects? So if you wanted to use something
Yeah.
in the world and,
Yep.
and animate it.
Yep. So yeah, that's totally the right approach. Usually people would take 3D scan it. Like you can use Kinect in order to do a scan. You combine that with some video. You'll get usually a pretty ugly model, but it's sort of something you can start with. What artists would usually do is immediately retopo it because it's just a mess to work with what you get out of the scans. So you run the retopo, now you have a nice mesh. Then you might go in with the sculpting to clean it up a little bit more and iterate on it. And then you could add a rig and you'll have a animated version of yourself if you scanned yourself. Yeah. So who wants to compile Blender?
Actually, I want to ask about that. So I saw online it's you're supposed to be able to compile as a library, but I tried and failed.
Compile which is a library?
Blender.
Oh, really? Okay, I didn't know that.
Oh,
Not compile as a library.
Okay.
I know who to talk to figure that out. So what were we trying to use it for?
I actually was wondering my research, and I got pretty fed up with the in Blender REPL. So I just
You can definitely run it without making the GUI. Like you can skip the UI. Or do you mean making it as a
no,
shared
I mean,
object?
like when trying to figure out like how the API works. So, yeah.
That's a whole other discussion. Blender has like a pretty fascinating internal structure. Blender has been lovingly described as a struct visualizer. It's literally like a bag of structs that are then rendered, and the format on disk is actually just like the dumbest possible serialization of these structs to disk. The header files in Blender that describe these structs are actually what are used. There's a parser that reads the header files that then generates the serialization format. So it's kind of hilarious. And you look at the code and you're like, oh, now I understand what that guy was talking about when he said it's a struct visualizer. Like it's kind of weird, but it kind of works. Yes. Oh.
A follow-up question.
Sure.
So what do you mean by it's a different description? So it's difficult to use it as a library without the GUI?
Well, so Blender is used for all sorts of rendering as part of a render farm. So there's a lot of people who use Blender in a headless mode where they just give it a blend file, say advance to frame 75, render 4 frames, and quit. That's pretty straightforward to do. If you want to make Blender into a shared object that you can load into your existing binary and then call things like the Blender loader to pull up your file from disk, expand it into in-memory structs, and then start operating on it, I don't know how easy that is to do.
Speaking of that, is there a way to run the game engine headless? So there isn't. There isn't. Okay.
Yeah, it's just not my area. Yes.
Since you've been with the project for a while, I was wondering, do you have an opinion on how this kind of projects should deal with backward compatibility?
It's an excellent question.
I've had an interesting experience recently where I opened Blender files that I made like in 2005 or something, and my particles were just all over the place, but it has nothing to do with my origin.
Yeah, it's a hard one. So on one hand, it'd be ideal if you could maintain complete backwards compatibility forever, but it's really hard. And sometimes you can end up in a situation where if you maintain backwards compatibility forever, it will cause you to not make as much forward progress. So it's kind of a trade-off. With that said, Blender actually has a lot of hooks to prevent obvious breakage when you load old files. It's actually supposed to be both forward and backward compatible. So that earlier I mentioned that Blender is a struct visualizer and that the file format is really just a bunch of structs from header files kind of concatenated together. So every Blender file has as the first part of its file this description of what all the structs are. And then the loading code is able to say, okay, this file was created in a Blender that had structures that look like this. And the Blender that is operating operating right now has a different set of structures, and it's able to say like, okay, the vertex structure in this one point value for X. The vertex structure in this one is a double. I know how to deal with that. I'll just convert it down and lose some precision, so it'll do that conversion. And maybe the new struct has an integer value for something, and it'll just default it to 0. Sometimes you have to write code in the loading part of Blender in order to override the behavior of the serializer to do something custom so that it'll kind of make the old code work. But the short answer is it just doesn't always work. Like sometimes there's massive refactorings and you just can't really map it. Some of the production files from the early open movies, you just can't really, they just won't open in modern Blender. The way they work around this is that well, sometimes you just have to recreate it. Sometimes they can export it to other formats and bring it back in through a different chain or channel. But like for example, right now they're redoing the whole dependency graph system where it's able to say things like, this finger is attached to that bone, is attached to this wrist, and how it all, there's computed properties and whatnot. That whole system is getting totally redone, and unfortunately it's going to break a lot of existing stuff. The new system is infinitely better than the old one, but there's just no way to fix some of these old rigs. Like people used to rely on bugs in the old code to make things work, and so if you're relying on buggy behavior, you just can't handle that. Yes.
The physics simulation that you mentioned, is that, I've heard that you could input in Python. Is that the best way or the other ways?
I don't really know much about the physics simulation, other than it's done with the Bullet engine, and there's some options around baking, so you can run a simulation, bake it so that it's stored. But